Welcome back to part 3 of the talk, A Fresh Approach to Teaching Optimization from Deterministic Optimization to Sequential Decision Problems. This is part 3, Designing Policies. I'm Warren Powell. So let's first ask the question, what do we mean by a policy? So a policy is a method that makes a decision using the information in the state variable, any method. So far, I've come up with 49 ways to say policy in the English language. All of these words in the right context means this is how to make a decision. Now, I like to build a bridge between searching for policies and sequential decisions and vanilla machine learning. Now, in machine learning, we're searching over functions. I'd like to find the best function. We often call it a model to fit the data. In sequential decisions, we're also searching over functions. We call them policies. Now, in machine learning, we have to have some big data set to fit the function to the data. The function itself doesn't actually know anything about the problem. The only information about the problem itself is in the training data set. Now, in sequential decision problems, I don't have a training data set. I do have a model on the underlying problem. And this is the core difference between sequential decisions and machine learning, but it helps to go at sequential decisions from the background of machine learning as opposed to the background of deterministic optimization. So how do we search over policies? So there's two fundamental strategies for designing policies. The first one I call the policy search strategy, and the second one is look-ahead approximations. Each of these two strategies can be divided into two classes, which create what I call the 4 classes of policies. Let's start with policy search. Now, PFA's, policy function approximations, are the simplest. Could be simple rules like order up to inventory policies, buy low, sell high. But a PFA can be any function used in machine learning. It just has to be some analytical function that when you input the data, out comes the decision. So here's an example, news vendor problem. This is one of the favorite problems of anybody doing stochastic optimization, academia, or operations management. And there's a little bit of math here where we can optimally find the optimal X of how many newspapers to put in the bin. Now, this is an actual email from a student at a major MBA program, and I'm not going to go through and read the email. I'm going to break it down. So the email starts, Professor, the news vendor inventory problem we learned in class looks like a way to optimize how much cash I should hold in the mutual fund I manage. Okay, so the basic problem is mutual funds hold a certain percent of their assets in cash to meet redemption requests. If we hold too little, redemptions may force us to liquidate prematurely. If we hold too much, then we might miss out on investment returns. But of course, this is the real world, so there's various complications. The stochastics are complicated, there's correlations. He's not sure if he can reduce it to a single time period, and I can say yes, he cannot. There's both retail investors and institutional investors, and what he realizes at the end of the day that his significant investment in that MBA actually hasn't taught him how to solve this problem. And so he's saying, hey, professor, do you know any references that will solve the problem? So this student was taught a stylized problem, the news vendor problem, which the professor solved in class, and I, among many of my colleagues, have all done the same thing. The student was not taught how to think about the problem in a way that allowed him to go after real-world problems in practice. And I'm going to say, fellow academics, shame on us. But I'm going to show you how to fix this. So there's a hint of how to solve the problem right here in the guy's email. Look at this sentence. Mutual funds hold a certain percentage of their assets in cash to meet redemption requests. So, well, there's the equation. So the policy could be a parameter theta times the number of assets, and now I just have to look for the right theta. But maybe I could try a different policy where, you know what, maybe I should divide the assets between the retail assets and the institutional assets and do a different function. And probably other people might be able to come in and say, oh, I can tweak this in various ways. But each of these are policy function approximations. They're analytical functions that input the data, such as the number of assets, and an output. But you have to tune it. You have to fix those thetas. Now, how do we simulate the policy? One very common way that finance does a lot is do backtesting using historical data. The nice thing is that all the redemption requests and whatnot will be independent of how much I'm actually holding. Now, I could create a mathematical model. Now, that would be a significant exercise, probably not something that somebody in industry could do, but something that a firm could create a product. But here's another way: do it in the field. Use online learning where you do trial and error. Now, that's not a trivial problem because you have to learn how to adjust the thetas. You have to try things which are in the field, which means if you try a bad value, it may cost you. The hardest thing is you might have to take a week or multiple weeks just to evaluate one setting, and even then there's still going to be quite a bit of noise. Okay, second class, cost function approximations. So these are parameterized optimization problems, widely used in industry. Uh, find the shortest path to a destination. Not only do I have to find the path, I have to decide when to leave, how much time to allow. Maybe Google Maps tells me to allow 40 minutes, but because of random traffic delays, maybe add in 15 minutes. And when I do the same trip over and over again, maybe the 15 is too big or too small. Maybe I schedule nurses for 36 hours a week, although they work 40 hours a week, because things come up and I need some buffer in the schedule. Now, here's a popular one. All the e-commerce companies, they have to pick when somebody logs into a website, I want to put ads that are interesting for that user. Now, I want to pick the ad, the product X, and I'd like to put up the one that will earn me the most ad clicks or the most revenue. And my estimated revenue is just an estimate, and it may be a pretty poor estimate. So what I'm going to do is take the estimated revenue plus theta times the standard deviation of the estimate. This is an optimization problem. Okay, no fancy algorithm here, it's a sort. But I have to determine theta. If I put theta equal to 0, then I'm just taking the best estimate. And again, if I had a run of bad luck and it's low, I may never try that product again. Now, in part 2 of my talk, we said, hey, what about this linear program that I'm going to solve at time t? Now, recognizing that I'm not going to solve it once, I'm going to solve it repeatedly, I'm going to throw in some tunable parameters to make it work well over time. This is my policy. And here I'm going to simulate my policy by solving sequences of linear programs that are tuned to work well over time. I will do this repeatedly as new information comes in. I'm simulating my policy. The policy, yes, involved solving a deterministic linear or integer program. And what I would like to do is tweak and tune the model, which is my policy, to get the policy that works best over time. This is widely used in industry. Airlines optimize their schedules with schedule slack. Manufacturers use buffer stocks. I learned this from watching grid operators that run the power grid, because they will sit on one day, Monday, plan for Tuesday, and to handle the uncertainty, which is today mainly in the form of generators breaking down, they have to schedule buffer reserves. Now, they solve a deterministic problem, but they put in a tunable parameter. This is absolutely a solid way, completely overlooked by industry. So I've given it a name, cost function approximations, and formalized it. It's in the same class. Think of it as like doing parametric modeling in machine learning. I think it's a powerful strategy, and we should embrace it as something that you put in our toolbox. Now, both PFAs and CFAs have tunable parameters that have to be tuned. So we can write that out mathematically. Now, one challenge is that whether I'm simulating or working in the real world, these simulations are noisy. Now, I can try to optimize this in a simulator if I have time to write a simulation, or we can optimize in the field. This is called learning by doing. Now, we can do the search using derivative-based methods. Usually that's in the event that I actually have built a simulator. But maybe I can do derivative-free optimization, or I do hunt and peck. There's a whole series of algorithms, often referred to as derivative-free stochastic search, but there's a whole community that calls these multi-arm bandit problems. Okay, let's go to the second category, look-ahead approximations. This is where I'm going to make a good decision by approximating the impact of the decision now in the future. Once again, this divides into two classes of policies. I like to view this as Dorothy in The Wizard of Oz trying to find her way to to the city of Oz. Now, we're going to have to address this big, very messy, ugly equation. Here we have the immediate cost of making a decision now, and then I have all that downstream ugliness. And we'll look at that and go, okay, wait a minute, I just can't compute that. I shouldn't do this at all. and not so fast. We can't run away from this because there's some problems where we just have to work with this. Now, I can write this out as a decision tree where I start off with that first square. That's my state. That's the place where I have some information, and I have decisions X. Now, X can be a vector. X can be a large high-dimensional integer program. I want to find the best X. Now, after I make the decision X, random stuff happens. I'd like to take expectations over that. And then again, I have all that messy stuff. Now, that messy stuff, I have decisions in the future where, once again, I have to make decisions. And then I have the random outcomes. Now, remember, I know that a lot of people have seen decision trees where this is always low dimensional. In my world, absolutely not. X can be very high dimensional. The random stuff can be very high dimensional. Now, the first of the two classes with look-ahead approximation says, hey, there's this function in there that whatever in there, it's some function, let's call it a value function, that depends on the state st plus 1. That's a value function. This is the foundation of the field known as Markov decision processes. This is what Bellman introduced. He made the assumption that the state was something discrete and that there's not very many of them, maybe a few tens of thousands, but not billions. And by the way, for very large complex problems, not only is billion very small, often these state variables are continuous, and so I don't even have discrete states. But so what I can do is turn to approximations, and there's various strategies. This is my book. What I've done here is I've gotten rid of the expectation by using the post-decision state, and I'm going to use machine learning methods. Now that argmax is a deterministic optimization problem, which opens the door for X to be something very high dimensional, such as assigning drivers to loads, which is something that we do at my company, Optimal Dynamics. Now, I have to assign drivers to loads, but I have to think about the impact of decisions now over time. Now, solving this over time deterministically is already hard, but the future is highly stochastic, and now I have a real mess of a problem. What I'm going to do is approximate the downstream value of drivers using a value function approximation. This turns the Monday problem into a fairly nice, simple problem. It's actually quite easy to solve. Now, it's so easy to solve that I can run simulations. So I set up the problem for Monday, I solve it in a few seconds, I step forward, simulating. Now I can run the simulation over and over again, and that's how we fit the value function approximations. Here's actual data from 11 different carriers, and over the training iterations, we get a nice improvement in profits. We start at time 0. That's where all the value functions are 0, so that would be a myopic solution, whereas out there in the future, and we get optimized VFAs, and we get a nice improvement in profit. Here's one animation of a large company that I was working with. By the way, each one of these little triangles is a truck driver with all of the complicating information that goes with managing a human being. Now, the final class of policy is, I call it the direct look-ahead approximations. This is where you make a decision now by planning into the future. You actually have to fully plan into the future. And you need what I refer to as a look-ahead model. Notice that I've put tildes on all the variables. So I have my base model. It has state, decision, information, state, decision, information. That's my base model. It could be a simulator. That could be my base model. But it could also be the real world. And then I have my look-ahead model where I also have state, decision, information, but I've probably approximated. I almost always approximate. That's why I've put tildes. Notice that they all have 2 time indices. The first t is because I'm making the decision at time t, and the t prime, is the time period in the future as I plan into the future. So what I can do is that approximate model, there's all different ways of doing approximations. I can approximate the stochastics. I can use a simplified policy. I can simplify the state variable. I can simplify the decisions, or even simplify how I make decisions in the future. It's a look-ahead problem. I just have to capture the core properties. So here let's say I come up with a good approximation. I look forward, make a decision now, update everything, roll forward, make a decision now, update everything, roll forward, make a decision now. A good example of this is something that we all do, Google Maps. So let's say I'm making a long trip. So I'm up in upper right-hand corner is Hartford, Connecticut, trying to make my way home to Princeton, which is in the lower left-hand corner. And there's Google saying, oh, here's this great path. By the way, it goes right through New York City at 5 p.m. Now, this is a deterministic look ahead. The controls people like to call this model predicted control. By the way, actually, all look ahead models are model predicted control, but the MPC literature usually assumes deterministic. So this is the most standard way of doing it. Now, I looked at this and I said, okay, so Google Maps gives me some alternatives, and I'm looking at that path going through New York City and going, Google, you've got to be kidding me. I'm not going to go through New York City at 5 o'clock in the afternoon. Now, this is me using a form of what the academic community likes to call robust optimization. Maybe I could get through New York City very quickly, but it might be really bad. And because I'm worried about the worst case, I route it around. That is what's known as robust optimization, but I could use stochastic programming or approximate dynamic programming for my book. Notice that these are 4 entire books dedicated to solving a look ahead policy. And they'll often say, oh, this is a problem, but most of the time it's not. It's a policy. It's a look ahead and it has to be repeatedly solved over time. Okay, I have now gone through the 4 classes of policies. The policy search policies are the simplest. These are the ones most widely used, the PFAs and the CFAs. The look ahead policies are the ones more complicated. 3 of these 4 classes of policies involve embedded optimization problems. And this can be very confusing because these 3 classes of policies, I have to optimize. Now, maybe the optimization is nothing but a sort, but it could be a big integer program. Now, I've gotten to a very nice place. I'm going to make a big claim. These 4 classes of policies are universal. They cover every method for making decisions described in the research literature or used in practice, even if it hasn't been invented yet. These are meta classes. So this means you're already using at least one of the 4 classes of policies in whatever you're doing as a human or as a project with a company. You're already in one of these 4 classes of policies, or a hybrid. Now, there's entire academic communities that are utterly buried in one of these 4 classes, sometimes a subclass for the direct look aheads. However, if you know all 4 of them, now you can start putting hybrids together. And I really think that we need to be teaching this to our students. Now, here's a little basic energy storage problem. I had a lot of fun with this problem when I was still teaching. So I can get energy from a wind farm. The energy is free, but there's a finite amount of it and the wind blows. I can get energy from the grid. Let's assume that's infinite, but the price of energy from the grid is stochastic, and so that's very messy. I need to meet the demand of a building or a campus or an entire city. And of course, I'll have my big Tesla Megapack to help absorb the buffers. Now, forecasting wind, this is real data. This is 24 hours. The black line is the actual wind. These updates, that first line is my forecast as of midnight, and every subsequent line is the updated forecast. And you can see it changes a lot. Forecasting wind is hard. And by the way, I have upper bounds. I have capacity constraints on my ability to transmit. So what am I going to do? All right, I'm going to do a deterministic look ahead. Honestly, I've actually worked on this problem quite a bit, and I come back to this. No, a deterministic look ahead really is going to be the best way. Now, buried in there is that crazy forecast. So I'm treating that forecast of energy as if it's a deterministic number when I know that it's really terrible. So how am I going to fix that? Okay, I'm going to be like a machine learner. I'm going to parameterize this model. I'm going to throw in a coefficient. Now I have a parameterized linear program. It's a look ahead and parameterized. So this is a hybrid. This is a direct look ahead, parameterized. Now, very easy to solve. So it's no more difficult to solve. It's just a deterministic LP. I can solve it in an eye blink. I look forward, make a decision now, roll forward, update the forecast, update anything else that I didn't know, solve it again. Keep doing this over time. Very easy to implement. The beautiful thing here is it's no more complicated to implement than your original deterministic model. Now, once again, as we were doing before, my policy is a deterministic linear program. The objective function is a simulation where I'm simulating forward over time. I have a stochastic optimization problem, which is So not only do I have to tune the parameters, maybe my parameterization isn't necessarily the best one. By the way, anybody starting a career, this is a fabulous area of research. We need a lot more work on this. This work, by the way, was joint with Saeed Gadimi, a very talented postdoc I was working with at the time. Now, what Syed recommended is we did a stochastic gradient algorithm. We had a simulator, Jim Spall's SPSA algorithm. You could do numerical derivatives, and we got very good results from this. Now, the first thing we optimized just to test, so we said, okay, let's say all the forecasts are perfect. And so we optimized the theta, and guess what? They all came out equal to 1, which, sigh of relief, okay, that's what we would have expected. So if I have a perfect forecast, the optimal thetas are in fact equal to 1. So what if we go to the stochastic forecast? Now we've got ourselves a bit of a mess. That line is for the theta for 1 hour out. Notice I have a different theta for 1 hour out, 2 hours out, 3 hours out, 4 hours out. That cluster up there is the next 4 hours. Very interesting, and the rest is everything else. If I set theta equal to 1 and call that the baseline, I plotted the percent improvement, and this is all done from different starting points, and I averaged about a 30% improvement. Now, this was not easy work to do. Tuning is not easy. We need, astonishingly, more research in this. But once it's done, it's no more complicated than in the field. Imagine those two-stage stochastic programs that are so popular, that are so hard to solve in the field. This method is no more difficult in the field, but we have a tuning problem. Now, with another postdoc, Stefan Meisel, Stefan created 5 variations of this energy problem, and we played around it. We made the data stationary or more random or less random. We created 4 policies, one from each of the 4 classes, plus the hybrid, which is the one that I just showed you. And each one of these 5 policies ended up working best on one of the problems, which means there's no silver bullet here. Each of the policies will have data. Now, there are going to be problems where one of the policies really screams at you, and sometimes some of the policies, like the VFAs, are going to be very complicated to implement. Now, let's go back to my bridging of machine learning and sequential decisions. So in sequential decisions, I have the PFAs. PFAs consist of any function that you might use in machine learning. If I restricted myself to the PFAs, this is just like machine learning. The only difference is I don't need a training data set. I do need a model of the problem. Okay, but that is only one of the 4 classes of policies. The other 3 are the ones that all have an embedded optimization problem. So the PFAs would never be able to handle a vectored value x, or at least anything with modest to high dimensions, whereas the other 3 can. And so this is where I can use powerful tools like my deterministic solvers. And by the way, most of these optimization problems are using deterministic optimization solvers to solve a stochastic optimization. Not all of them. The direct look ahead, if you have a stochastic look ahead, you might end up using still have to do a stochastic optimization problem. Now let's go back to all these books that the academic community teaches, and let's take a look at how many of them use Bellman's equation. And the answer is most of them, especially mine in the upper right-hand corner, okay? So 15 years ago, that came out in 2010, I would have been, oh my gosh, ADP is great. So I'm older and wiser, and I know now Bellman's equation is much harder. Now, if you're not using Bellman, people really like the look-aheads, especially stochastic look-aheads. And so these books mainly are doing some form of stochastic look-ahead. Now, let's take our 4 classes of policies. I'm going to divide the 4th class into 2 types, deterministic look-ahead and stochastic look-ahead. Now I have 5 types of policies, and we can stand back and say, hey, which ones are the most useful? All right, from my decades of experience, category 1, I have 3 types of policies, the PFAs, CFAs, and deterministic DLAs. I claim these are your big 3. This is by far the ones most widely used in practice. So all those urban professionals on the street that I showed in part 1 of the talk that make decisions, this is what they're using, okay? I claim all humans already use these when we make decisions. We're just not aware of it. Now, category two, stochastic direct look ahead, I'm really thinking decision trees here. Okay, I am not thinking two-stage stochastic programming. This is decision trees, and the simple reality is sometimes we have problems where we do have to think in the future, like me planning the path through New York City, going, oh my gosh, but it might be terrible. So again, we humans are aware that sometimes we don't know what's going to happen in the future, and we make various adjustments. Look at what I've put in category three. Now, I wrote a 600-page book. I spent 15 years of my life based on approximating value functions. I've got that down at the bottom as the least useful, although I would put it above two-stage stochastic programming. Policies based on Bellman's equation, I claim, is a very powerful strategy for a very small number of specialized problems. I would never teach this material into an introductory course, undergrad or master's, or even introductory PhD, other than saying, oh, here's Bellman's equation, we'll get back to that in an advanced course. It's just not that useful, okay? Once people really understand, because most of the research out there with Bellman's equation are people where it's the classic hammer looking for a nail. They take Bellman's equation and they find problems that they can solve with Bellman's equation. The real world does, and that's what I did for many years. The real world doesn't work that way. They have their problem, and you have to have a tool to solve their problem. Now, when we go back to bridging, let's go back once again, look at our machine learning. But on the right-hand side, now I'm restricting myself to parameterized policies. Now, machine learning, we have the human looking for the best function. Maybe I want a linear function. Maybe I want a nonlinear or a neural net. The parameterized function, and then I have to do the tuning. I have to fit the function. But the parameterized policies, let's take my PFAs, CFAs, and deterministic DLAs. These are also functions, and they all have tunable parameters. And I have to tune the parameter. I don't have a tuning data set. When I limit myself to the parameterized policies, now I'm really starting to behave like a machine learner, which I would think is very popular today. Okay, so that is my part three of my talk. Once again, I will point people to my resources URL, tinyurl.com, SDA links, has a number of resources of additional information.